Okay, good morning, all. Uh, Last class, we have seen about the Colpitt's oscillator. Uh, the Colpitt's oscillator is the oscillator which is used to generate the radio frequency, radio frequency in the range of radio frequency oscillations. Okay, and also we saw the circuit construction and operation and mathematical analysis. How to derive an expression for the frequency of oscillations, and then what is the condition for the frequency of oscillation. So these are the things which we have discussed earlier, and also we saw the what are the conditions for sustain the oscillations according to the Barkerson criteria. So what is the Barkerson criteria? How the Barkerson criteria is satisfied in this Colpitt's oscillator. Earlier to that, I have discussed about the Hartley oscillator. So both are similar. Only thing is the difference thing is tank circuit. Okay, in case of the Hartley oscillator, the tank circuit will made up of two inductors and one capacitor, whereas Colpitt's oscillator is made up of two capacitor, two capacitors and one inductor. That is the basic difference between these two oscillators. The frequency of oscillation, the formula for frequency of oscillation is similar. Of course, it is nothing but F is equal to 1 by 2 pi root over LC. In case of the Hartley, where L is nothing but L equivalent. In case of Colpitt's and C is nothing but C total or C equivalent. Okay, where L equivalent is nothing but L1 plus L2 plus 2M. Of course, we can neglect the value of M because the mutual coupling between the first inductor L1 and second inductor L2 is very negligible. That's why we have neglected that one. So the L equivalent is equal to L1 plus L2. Where Colpitt's oscillator, the formula is similar, but uh, C total, that is nothing but the C equivalent. The C equivalent is obtained by C1 C2 by C1 plus C2. C1 C2 by C1 plus C2. And this is a very important formula. So, while calculating the frequency of oscillation and to calculate the value of what is the value of L, what is the value of C for a given oscillating frequency for Hartley and Colpitt's oscillator. Okay, and also we have seen the conditions. In conditions means the beta. Beta is nothing but a feedback ratio. The beta should be C1 by C2 in case of Colpitt's, and in case of Hartley, that is nothing but the L1 by L2. Okay, for a oscillation to start, the voltage gain must be greater than 1 by beta. 1 by beta, that is nothing but the C2 by C1 in case of the Colpitt's oscillator and L2 by L1 in case of the Hartley oscillator. Okay, so phase angle, of course, we can get the phase angle 360. 180 degrees obtained by the transistor circuit. Okay, 180 degrees obtained by the transistor circuit. That is nothing but the we are using the transistor circuit as a C amplifier. The C amplifier produces 180 degrees phase shift, and another phase shift is obtained from the tank circuit of L and C. Of L and C. In case of the Hartley, L1 and L2 and C. In case of Colpitt's, L and C1 and C2. C1, C2. Okay. So because of we are at the middle terminal, we have the tank circuit. The tank circuit, we have identified the three terminals. We have kept the terminal 3 at a ground potential. Due to that ground potential, the terminal 1 is positive at any instant. At the same instant, the terminal 2 is negative. Okay. So by that way, we can get 180 degrees out of phase from the tank circuit. Okay. And the total phase shift in the closed loop is 360 or 0. Okay. We can obtain these two conditions. So I think up to this, all of you familiar with this circuit of the LC oscillators, that is nothing but the Hartley oscillator and Colpitt's oscillator, and then operation and construction of the circuit and operation of the circuit and mathematical analysis. So mathematical analysis, simply you take the generalized expression, so which consisting of the L1 and L combination of Z1, Z2, Z3. So simply you replace the value of Z1, Z2, Z3 as a capacitance as an inductor. Okay, according to the circuit. What is the circuit? For what circuit we are going to perform the mathematical analysis to get the frequency of oscillation. Then we have accordingly you have to substitute the value of L and Z1 and Z2 and Z3. Z1 and Z2 and Z3. Okay, this is about Hartley oscillator and Colpitts oscillator. So just we have gone through the earlier two classes. Okay, now we are going to move another important oscillator, which is nothing but the crystal oscillator. So what is a crystal oscillator? So what is the necessity to go with the crystal oscillator? Okay, and how this crystal oscillator will work. Okay, and this is the thing. These are the things which we are going to know under this unit. Okay, so under this topic particularly. Okay, so when the crystal, what is the necessity of the crystal oscillator? The necessity of the crystal oscillator came into the picture when a high degree of frequency stability is required. Okay, and a high degree of frequency stability is required, particularly over a long period of time. So then we use a tuned circuit of the oscillator. That the oscillator is replaced by the tuned circuit is replaced by the quartz crystal. Tuned circuit is replaced by the quartz crystal. Okay, so such a crystal oscillators are very useful as a master oscillator in radio transmitters. So these oscillators are very useful in a radio transmitters and signal receivers and test equipment and some communication apparatus. Okay, so this is the importance of the and the crystal oscillator works based on the piezoelectric effect. The crystal oscillator will work on the piezoelectric effect. Okay, so then what is a piezoelectric effect? How this piezoelectric effect will work? And then by using this piezoelectric effect, how the crystal works as a oscillator. Let we see. So what do you mean by piezoelectric crystals? So piezoelectric crystals are some materials. So in this type there are some piezoelectric crystals. So these are piezoelectric crystals are usually quartz crystal or some tourmaline crystal and Rochelli salt. So these are the different types of crystals which we have used as a piezoelectric crystals. So by among these three, so the most commonly used crystal is quartz crystal. Okay, in this type of oscillator, we are going to use the piezoelectric crystals. So usually quartz is used as a resonant circuit, replacing an LC in case of the LC circuit. Okay, so the certain crystal materials because of why we choose these Rochelli salt and quartz and tourmaline means these three materials will exhibit the piezoelectric effect. So then what do you mean by piezoelectric effect? What do you mean by piezoelectric effect? How these will be exhibit? How these materials will exhibit the piezoelectric effect? Okay, so piezoelectric effect means when we apply an AC voltage across them, means across the crystal, they vibrate at a frequency of voltage applied. If the crystals are forced mechanically to vibrate, they generate an EMF at the fundamental frequency of the crystal. Simply, this phenomenon is known as piezoelectric effect. Simply, this phenomenon known as piezoelectric effect. Suppose the crystal is a thin slice. We are going to cut this crystal as a thin slice of a piezoelectric material. So such as this either a quartz material or Rochelle salt material or tungsten material. Okay, tungsten material which exhibits the properties called as a piezoelectric effect. So what do you mean by piezoelectric means? The piezoelectric effect represents in the characteristics that a crystal reacts at any mechanical stress by producing an electric charge. Yes, that's the point I have told here. If we apply an AC voltage across the slice of the crystal, they may vibrate. They may vibrate at the frequency of applied voltage and the frequency of applied voltage. So what is the applied voltage frequency? So generally, suppose if you apply the AC voltage, the AC voltage generally the AC voltage is a 230 volts, 50 hertz. 50 hertz is the frequency. Okay, the AC voltage frequency is 50 hertz. When we apply this voltage, AC voltage across the slice of these above crystals, that is Rochelle salt crystal or quartz crystal or tourmaline crystal, then they vibrate at the frequency of the applied voltage. Okay, so simply if the crystals are forced mechanically to vibrate, forced to how we are going to force? So by applying an external AC voltage. So by applying an external voltage, we are going to force the crystal. The crystals are forced mechanically to vibrate. So when we are forced mechanically, they are generate an EMF. So what is the frequency of EMF? The frequency of EMF is the fundamental frequency of the crystal, which is equal to the applied voltage frequency, So because of it will generate the frequency at applied voltage frequency. Then we are going to increase by connecting the various elements. Okay, Nandi. So am I able to get all of you clear my point? Anybody can respond?
Yes, sir.
Okay, Namma.
Sir.
So చెప్పండి.
ఇప్పుడు మనం క్రిస్టల్ కి ఏసీ వోల్టేజ్ 50 హెచ్ తో ఇచ్చాం కదా, అదే అవుట్పుట్ లో ఈఎంఎఫ్ అని ఇండ్యూస్ అయింది. అది కూడా సేమ్ వోల్టేజ్ తో
ఒక్క నిమిషం నా మాట వినండి. అవుట్పుట్ లో కాదు, జస్ట్ మనం ఆ క్రిస్టల్ కి మనం వోల్టేజ్ మనం ఫోర్స్ ఈ వోల్టేజ్ అప్లై చేసి మెకానికల్ ఫోర్స్ ఇస్తున్నాం కదా, ఆ క్రిస్టల్ లో వైబ్రేట్ అవుద్ది ఆ ఫ్రీక్వెన్సీ. క్రిస్టల్ లో మొత్తం అవుట్పుట్ కాదు, అవుట్పుట్ హై ఫ్రీక్వెన్సీ. అర్థమైందా?
ఆయన డౌట్ ఏంటంటే మనకి ఇచ్చింది ఎంత వోల్టేజ్ ఇచ్చామో అవుట్పుట్ కూడా అదే ఆ క్రిస్టల్ వచ్చింది కూడా అంతే వస్తుంది. యూజ్ చేయలేదు సార్.
క్రిస్టల్ లో జస్ట్ ఫండమెంటల్ ఫ్రీక్వెన్సీ, అది ఫండమెంటల్ ఫ్రీక్వెన్సీ. దాని నుంచి మనం ఫ్రీక్వెన్సీ ఇంక్రీజ్ చేస్తాం బై కనెక్టింగ్ ది అదర్ ఎలిమెంట్స్. కెపాసిటర్లు కూడా కనెక్ట్ చేస్తాం.
కాకపోతే ఇచ్చిన వోల్టేజ్ ఎంత ఇచ్చామో ఆ క్రిస్టల్ నుంచి వచ్చింది కూడా అంతే వచ్చితే మరి దాని యూజ్ ఏంటి అడుగుతున్నాను సార్.
అంటే అది ఫండమెంటల్, అది క్రిస్టల్లో వచ్చేదే. దాని నుంచి మనం ఆ క్రిస్టల్ ఒకటే కాదు సార్, మన సర్క్యూట్ లో ఇంకా ఎలిమెంట్స్ ఉంటాయి. నీకు చిన్న ఎగ్జాంపుల్ చెప్తాను చూడు. ఇది చూడండి ఒకసారి. సర్క్యూట్ చూసారా? కనబడుతుందా సర్క్యూట్? ఇది మనకి కింద నుండి క్రిస్టల్. ఓకేనా? హలో.
ఓకే సార్. ఓకే సార్.
ఈ క్రిస్టల్ కాస్త C1 C2 ప్యారలల్ విత్ క్రిస్టల్ కనెక్ట్ చేసాం. గుర్తుందా? మనకి ఫోర్స్ అప్లై చేస్తే వచ్చేది ఇక్కడ ఫ్రీక్వెన్సీ. దీని క్రిస్టల్ ఫ్రీక్వెన్సీ, టోటల్ ఫ్రీక్వెన్సీ కాదు మనకి, ఇక్కడ అవుట్పుట్ ఫ్రీక్వెన్సీ కాదు. అగైన్ మనం ఈ ట్యాంక్ సర్క్యూట్ లో ఇన్ అడిషన్ టు దిస్ క్రిస్టల్ వీఆర్ హ్యావింగ్ సమ్ అదర్ మెటీరియల్, కెపాసిటర్స్. ఓకేనా?
ఓకే సార్.
సో బై యూజింగ్ దిస్ కెపాసిటర్స్ అండ్ క్రిస్టల్ ఏం చేస్తామంటే ఇనీషియల్ గా క్రిస్టల్ అడ్వాంటేజ్ ఏంటంటే మనం ఇనీషియల్ గా ఫ్రీక్వెన్సీ జనరేట్ చేయడానికి యూజ్ చేస్తాం. ఇనీషియల్ మెకానికల్ ఫోర్స్ అప్లై చేసి అక్కడ క్రిస్టల్ ఫండమెంటల్ ఫ్రీక్వెన్సీ, అది మొత్తం సర్క్యూట్ అవుట్పుట్ ఫ్రీక్వెన్సీ కాదు. ఓకేనా?
ఓకే సార్.
ఓకేనా? క్రిస్టల్ ఫండమెంటల్ ఫ్రీక్వెన్సీ అది జస్ట్ ఒకసారి స్టార్ట్ చేస్తామండి. సపోజ్ ఏదైనా స్టార్ట్ చేయడానికి కొంత అవసరం కదా, స్టార్ట్ చేసిన తర్వాత మనం స్పీడ్ పెంచుకోవచ్చు, తగ్గించుకోవచ్చు, అది మన చేతిలో ఉంటుంది కదా, బై డిపెండింగ్ అపాన్ అదర్ వాల్యూస్ కదా. ఏదైనా ఒక డివైస్ ఆపరేట్ చేసాం అనుకోండి, ఏదో మోటారే ఉందనుకోండి, ఇనీషియల్గా ఏదో కొంత ఫోర్స్ అప్లై చేసి దాన్ని స్టార్ట్ చేస్తారా? స్టార్ట్ చేసిన తర్వాత దాని స్పీడ్ పెంచాలా తగ్గించాలా అన్నది మిగతా ఎక్విప్మెంట్ మీద డిపెండ్ అయి ఉంటుంది కదా. అర్థమైందా పాయింట్ లేదా?
అర్థమైంది సార్.
అలాగే ఇనిషియేట్ చేయడానికి క్రిస్టల్ వాడతాం. అలాగని ఈ క్రిస్టల్లో జనరేట్ అయిన ఫ్రీక్వెన్సీ మన అవుట్పుట్ ఫ్రీక్వెన్సీ కాదు. ఓకేనా? ఈ పాయింట్ గుర్తుపెట్టుకోండి. క్రిస్టల్ ఆసిలేషన్స్ ఇనిషియేట్ చేయడానికి క్రిస్టల్ వాడుతున్నాం. ఆ క్రిస్టల్ వాడి మనం ఆసిలేషన్స్ స్టార్ట్ చేస్తున్నాం. అంటే ఇంతకుముందు స్టార్టింగ్ కండిషన్స్ ఏదో ఉండేది కదా మనకి, ఇలాగైతే స్టార్ట్ అవుతాయి స్టార్ట్ చేయడానికి. స్టార్ట్ చేసిన తర్వాత కానీ మనం ఫ్రీక్వెన్సీ మొత్తం మళ్ళీ కానీ సర్క్యూట్ కంప్లీట్ చేసిన తర్వాత మళ్ళీ యాంప్లిఫై చేసి మళ్ళీ వచ్చి మళ్ళీ ప్రొడ్యూస్ అయ్యేలాగా జస్ట్ వేరే అవుతుంది కంప్లీట్గా. అది వేరు. టోటల్ అది కంప్లీట్ అవుట్పుట్ మనకి. టోటల్ కంప్లీట్ అయిన తర్వాత వచ్చే అవుట్పుట్ టోటల్ అవుట్పుట్. కాకపోతే బిఫోర్ దట్ టైం వచ్చి ఇనీషియల్గా స్టార్ట్ అవ్వడానికి కండిషన్ ఇది. ఓకేనా? అది అడ్వాంటేజ్ ఆఫ్ ది క్రిస్టల్. చెప్తాను ఫర్దర్ దాంట్లో, నెక్స్ట్ దానికి వెళ్ళినప్పుడు చెప్తాను ఒకసారి. ఓకేనా? సో దిస్ ఇస్ if the crystals are forced to mechanically to vibrate, then they are generate an EMF at the fundamental frequency of the crystal. Okay, that is remember that point. They generate the EMF at fundamental frequency of the crystal. Further we are going to increase. Okay na? So this is a piezoelectric effect, or let me say this is a crystal. This crystal is applied with this voltage, current, and this resistor. Then a voltage, external voltage is applied. Then it is forced to vibrate with the help of this positive and negative plates. So these are the positive electrode and this is the negative electrode. Okay, and then it starts vibrating. When they start vibrating, it produces the EMF with a fundamental frequency. So that is nothing but piezoelectric effect. Okay, so removal of force releases the strain with the crystal, and hence the current flow to re-establish the zero potential across the electrodes. Okay, and then I will go with this theory. Okay, and yes, and before working of the crystal, how we are going to construct a crystal? The crystal is constructed by taking the, why we go for the crystal oscillator means in order to obtain high degree of frequency stability. In order to obtain the high degree of frequency stability, so we are go with the crystal oscillators. Generally, this is a ground wafer transparent quartz material or tourmaline stone or Rochelli salt material. So any of these is placed between the two metal plates and housed in a stamp size package. Then there are two different methods to cutting the crystal wafer. So here the cutting of the crystal wafer is very, very important. The cutting of the crystal wafer is very, very important. So we are going to cut this quartz material or Rochelli salt material or tourmaline stone material. So we are going to cut this material like a wafer, Okay, so this is the very, very important. Got my point? Okay.
Okay, sir.
Okay. Because of we are using crystal oscillator, the crystal oscillators are used the material. Yes, 1 minute, just a minute. Yeah. Before this working of crystal, let we see the equivalent circuit of the crystal. Yeah. So this is the equivalent circuit of the piezoelectric crystal. So this is the symbolic representation. We are going to cut this quartz material or tourmaline stone or Rochelli salt material as like this wafer. So this is the symbolic representation of the crystal. So this is the equivalent circuit. Of the crystal. Okay. Now the crystal reactance, how the crystal reactance varies according to the frequency. Okay, how the reactance of the crystal, what is the resistance for resistive part and the capacitive part, how this resistive and capacitive, inductive and capacitive parts varies according to the variation of, according to the varying the frequency. Okay, so here we are going to neglect the resistance. So this is the symbol and this is the equivalent circuit. The equivalent circuit consisting of series combination of LC or RLC in parallel with one capacitor. Okay, this is the series capacitor and this is the parallel. This is the parallel capacitor. Okay, so this is the equivalent circuit. The equivalent circuit of the crystal shown in the figure. The ratio of CB to CS. This is the CP and this is the CS. The ratio of CP to CS may be several hundreds or more than that. Okay, several hundreds or more than that. So this is the, so that the series resonant frequency is very close to the parallel resonant frequency. Okay, because of we are going to take the ratio of CP to CS. The ratio of CP to CS more than maybe several hundreds or more than that, so that the series resonant frequency is very close or very to parallel resonant frequency. So the resonant frequency is inversely proportional to the thickness of the crystal. The resonant frequency is inversely proportional to the thickness of the crystal. So the resonant frequency from 0 to or some 0.5 to 30 megahertz can be obtained by using this crystal material. The resonant frequency from 0.5 hertz to 0.5 to 30 megahertz can be obtained by using this crystal material. So this is the equivalent circuit. Okay, this is the equivalent circuit. So the reactance function, how can you get the value of the reactance function of this crystal by using this figure? The reactance function of this figure C, if you consider this reactance function, the reactance function is obtained by Jx is equal to 1 by j omega p Cp into omega square minus omega s square by omega square minus omega p square. So this is the, sorry, yeah. So we can get the reactance function of this figure. This figure, the reactance function of this figure can be obtained by using the formula Jx. Jx is equal to 1 by omega Cp into omega square minus omega s square by omega square minus omega p square, where omega s is the series resonant frequency and omega p is the parallel resonant frequency and omega is the resonant frequency, and Cp and C, parallel capacitance and series capacitance, parallel capacitance and series capacitance. Okay, we have to maintain the ratio of Cp to Cs, that may be several hundreds or more than that. We have to maintain the ratio of Cp to Cs, maybe several hundreds or more than that. So because by maintaining the ratio of the Cp to Ce more several hundreds, so that the series resonant frequency is very close to the parallel resonant frequency. The series resonant frequency is very close to the parallel resonant frequency. Okay, so this is the equivalent circuit and this is the symbolic representation, and this is the variation of the crystal reactance according to the inductive and capacitive values. So this is the series resonant frequency omega s and this is the parallel resonant frequency. See, at this particular point, the series resonant frequency and parallel resonant frequency both are similar. Okay, at this particular point, at this particular omega, the series resonant frequency and parallel resonant frequency is similar. Okay, why? Because if we maintain the ratio of omega Cp to Cs, by maintaining the Cp to C ratio of Cp to Cs in order of several hundreds, then we get the parallel resonant frequency and series resonant frequency very close. Parallel resonant frequency and series resonant frequency are very close. Okay, yeah. And the crystal is vibrating its equivalent electrical circuit. Then the capacitance value Cp and Cs are very low. Cp and Cs are very low. So at low frequency, the impedance of the network is high and the capacitance is like this. Okay, the impedance is high and the capacitance is low. Okay, at that particular frequency. So this figure shows that point. Okay. And the frequency response of the crystal, we can get the frequency response of this crystal by the frequency response is increased in RLC branch approaches its resonant frequency. So in equivalent circuit, this branch, this arm, because of these two arms are parallel. This RLC, R is of course R is very small, R, CS and L. So this the value of this one RLC branch approaches the resonant frequency. We are going to increase the value of as the frequency increases, the RLC branch approaches its resonant frequency. At some definite some particular frequency, the reactance of XL will be equal to the XCS. The crystal is now acts as a series resonant circuit. Okay. So this is the frequency response of this. Now we are going to see the circuit operation. So how we are going to construct a circuit? Okay, what is the circuit of the crystal oscillator? If you observe this figure, so of course it is consisting of the two parts. One is the amplifier part, another one is the tank circuit part. One is the amplifier part, another one is the tank circuit part. The amplifier part is nothing but again C amplifier, which is made up of one N-pin transistor and R1, R2, C. This is CB, CE, and CC. Coupling capacity is of course not mentioned here. So this R1 and R2 provide the proper biasing to the transistor, and this RF is choke. Opposes interference by it is used for the isolate the interference between this DC voltage and this output frequency, the output frequency. So that is the purpose of this RFC radio frequency. So again this R1 and R2 use it to provide the proper biasing, and C in RCB blocking capacitor, this blocking capacitor input capacitor use it to block the DC. If there is any DC part is come across this input, then it blocks the DC and it allows the AC. And if there is excess voltage, this excess voltage is given to the ground by using this. Of course, it is a grounded. This terminal is grounded. RE is grounded. Okay, ground, and then this is the voltage protection for the high. This RE is kept for the high voltage protection for the transistor. If the high voltage is appears across the transistor, the transistor will get damaged. For that purpose, we are going to keep this value of RE. Of course, this entire operation is nothing but a simple C amplifier operation. Okay, C amplifier operation. Then another circuit is nothing but the tank circuit. The tank circuit, if you look at the tank circuit, it is similar to the Colpitt's oscillator. Okay, it's similar to the Colpitt's oscillator. In case of the Colpitt's oscillator, we have taken Z1 as a C1 and Z2 as a C2 and Z3 as a L. Z3 as a L. So instead of Z1, Z2, Z3 as a C1, C2, L, we have replaced the value of L by a quartz crystal. We have replaced the element L by with crystal material, by with a crystal material. So hence it is also called as Colpitt's crystal oscillator. Hence it is also called as Colpitt's crystal oscillator. If you clearly observe this tank circuit, the tank circuit is almost similar to the Colpitt's oscillator circuit. In case of the Colpitt's oscillator circuit, we are using Z1 as a capacitor and Z2 as a capacitor and Z3 as an inductor. Okay, the circuit is similar to the Colpitt's oscillator except one thing. What is that difference? So instead of L, we have replaced the value of L by a quartz crystal material. This is Xtal. Xtal is nothing but crystal. Okay, I mentioned here X, capital X, EAL. Xtal means it is a crystal. So in case of the Colpitt's oscillator, Here we are have an inductor. The inductor is replaced with a crystal material. Hence, it is a Colpitt's crystal oscillator. Colpitt's crystal oscillator. Why? Because in this Colpitt's oscillator, the inductor is replaced by the crystal. The inductor is replaced by the crystal. So of course we have discussed the crystal material in this type of a piezoelectric crystal, that is usually quartz crystal. Of course there are three different crystal material: Rochelle salt and tourmaline stone and quartz material. So in the most commonly used crystal material is a quartz crystal material. In this we are going to use a quartz crystal material. So this is the circuit construction. The circuit construction is very simple. You familiar with the circuit diagram of the Colpitt's oscillator. So it is almost similar with the Colpitt's oscillator. Only thing is the inductor is replaced by the crystal. Only thing is the inductor is replaced by the crystal. That's why it is also called as Colpitt's crystal oscillator. Colpitt's crystal oscillator. Okay. Able to all of you able to get the construction of the crystal oscillator circuit? Anybody can respond? Am I able to get?
Yes,
Okay. Construction అర్థమైంది కదమ్మా. సర్క్యూట్ కాల్పిట్స్ ఆసిలేటర్ సర్క్యూట్ రాజేయగలరు కదా. ఓకేనా?
sir.
క్రిస్టల్ ఆసిలేటర్ సర్క్యూట్ ఇట్ ఈస్ సిమిలర్ టు ది కాల్పిట్స్. ఓకేనా? ఓకే.
Okay, sir.
Right. Also, we have to remember the equivalent circuit. What is that equivalent circuit means? That yes, the symbolic representation of the crystal and equivalent circuit. And then, if you look at the figure, it shows the crystal, the symbol of the crystal. If you look at this figure A represents the symbol of the crystal, and the figure B represents the equivalent circuit of the crystal, and the figure C represents the crystal reactance versus frequency. The graph, that's the graph of the crystal that is drawn between reactance versus the frequency. Reactance versus the frequency. Okay. If you observe this figure, the crystal has a resonance as well as the crystal has a series resonance or parallel resonance. Okay, because of we have connected here, one is parallel capacitor and another series capacitor. So in this equivalent, if you go through this equivalent circuit, you look at this figure, the crystal shows that it has a series resonance as well as the parallel resonance. Series resonance as well as the parallel resonance. The three elements RLC. Okay, RLC are the characteristics in the if you observe this equivalent circuit. So this is a R and this is a CS and this is a L. Okay, the three elements RLC are the characteristics of the natural crystal, and CS, CP. CP is the capacitance of the two electrodes supporting the crystal. Because if you observe this figure, this is the crystal material. We are going to apply some electrodes. So these electrodes are nothing but the CP. The capacitance between this electrode and this electrode is nothing but the CP. And in this material, there is a resistance, capacitance and inductance, RLC. Okay. So the same thing I have drawn the equivalent as an equivalent circuit like this. An equivalent circuit. Yeah, like this. Okay. So the three elements RLC are the characteristics of the natural crystal, and the CP is the capacitance of the two electrodes supporting the crystal. So suppose we are going to operate the crystal as an oscillator, the crystal has to supported by these two electrodes. If you observe these two electrodes, one is the positive electrode and another one is the negative electrode. This positive electrode and negative electrode capacitance is Cp. Okay, because the capacitance between these two electrodes is Cp. Okay, the Cp is the capacitance of the two electrodes, with these two electrodes supporting the crystal. Okay, these two electrodes supporting the crystal. Am I able to get my point? Are you able to get my point? Okay, so then it can be observed easily from this reactance characteristics. If you observe the reactance characteristics of the crystal, okay, that the crystal is capacitive up to series resonance frequency. See, listen, if you observe this in this curve, it is nothing but the graphical representation of the crystal reactance versus frequency. The crystal reactance versus frequency. If you observe this curve, crystal capacity, the crystal is a capacitive up to series resonance frequency. Okay, if the frequency is so this is the frequency axis actually. X-axis is the frequency axis. Okay, if we are going to increase the frequency, so this is the capacitance of your crystal. This is the reactance part. So the reactance of the crystal is in capacitive in nature. The reactance part is, so we are like low frequency, means so 0, and then we are going to increase it from edges like this, and so on. If the frequency is equal to the series resonance frequency, up to that frequency, your crystal will exhibit a capacitive in nature. Capacitive in nature. Okay. Okay, Randy? The reactance characteristic, the crystal is a capacitive up to the series resonance frequency. If you observe this third figure, figure number 3, okay, so this is the y-axis is the reactance part and the x-axis is the frequency. If we start with the 0 frequency, of course the reactance is capacitive reactance, then we are going to increase the frequency. The reactance, so the capacitive reactance start decrease, and then if the frequency is equal to the series resonance frequency, W is equal to Ws, up to this, it is a capacitive. It is a crystal is a capacitive. Okay, and above that frequency, then it is parallel. Above that frequency, above the parallel resonant frequency, then it exhibits the inductive nature. Inductive nature. So up to this parallel resonant frequency. So it is inductive nature. So this is the graphical representation of this one, and from this we are going to get the impedance of the crystal. The impedance of the crystal can be obtained by Jx is equal to 1 by Jx is equal to 1 by j omega Cp into omega square minus omega f square by omega square minus omega p square. Omega s square minus omega p square. So I will give the material. So we will go through that formulas. Okay, so it is difficult to type that equation in this slide. I will give the material and go through that material and study. Then observe the reactance function, the reactance function of the crystal. Okay, so by neglecting the value of R, we are going to neglect the value of R, and then here the value of omega s square is equal to 1 by L into S, L into Cs, 1 by L into Cs. Now from this we are going to find the value of the frequency of oscillation of this crystal oscillator is 1 by 2 pi into L1 plus L2 into C. L1 plus L2 into C. Okay. This is the frequency of oscillation. The frequency oscillation frequency is 1 by 2 pi into L1 plus L2 into C. Okay. Okay, you will go through this equivalent circuit. The equivalent circuit of the crystal has go through this material. I will supply you, and then find the equivalent circuit. After that, frequency response. The frequency response is like this, and this is the frequency of oscillator. L into CS, sorry. The frequency response of the crystal is the condition impedance of the crystal. The frequency response vibrating the crystal is the series resonant frequency. Already resonant Fs is equal to 1 by 2 by L into CS and okay, L into CS. This is the frequency response of the crystal. Of course, we have discussed about all these things there. Yeah, this is the frequency. Formula for frequency. Derivation is not necessary for this one. Simply remember the formula for series resonant frequency and parallel resonant frequency. A series resonant frequency is given by this formula. Fs is CS into Cp by Cs plus C. So this is the frequency. Okay, of course we saw the circuit diagram construction and operation. Okay, this is the transistor crystal oscillator. Circuit the same as with the, of course I told you, the circuit is same as with the Colpitt's oscillator. Only thing is L is replaced with the crystal. L is replaced by the crystal. Okay, of course the positive feedback is provided by the capacitive voltage divider network, and then because of again phase shift, C amplifier produce 180 degrees phase shift, and this the combination of the C1 C2 produce the another 180 degrees phase shift. So total 360 degrees phase shift is maintained in the circuit to satisfy the Barkhasan criteria. Okay, of course you know the purpose of the resistance R1 and R2 and RE for the stabilization for provide the proper biasing. Okay, this is the C amplifier configuration, produce 180 degrees phase shift. Okay, the remaining phase shift is provided by the feedback network. So these are the some crystal oscillators. These are the some used crystal oscillators which are used in the laboratories as well as the some industries. Okay. Yeah. This is also one kind of crystal. Okay. This crystal, this type of crystals are used at the 10 megahertz to 50 megahertz range. Okay. 10 megahertz to, this is the symbolic representation. Of course, we saw, this is of course we have seen. This is the equivalent circuit, which we have seen earlier, RLC. See, this is representation, notation is different for the different others. We consider this is a CP and this is a CS. CP and CS. Of course, R is a very negligible small RLC. Yeah, yeah. RLC is parallel with one capacitor, that is nothing but CP. This is we are going to apply an AC voltage for this. Okay, now coming to the applications or advantages. The crystal oscillators can produce the highest oscillating frequencies. The quality factor of the crystal is very high, and these crystal oscillator have a high order of frequency stability, the low cost, and simple construction. The construction is very simple. It seems to be simple C amplifier and capacitor, two capacitors on crystal. Disadvantage: the slit crystal oscillators are they are less fragile and consequently can only be used at low power circuits. As high power circuit, low power circuits. These are some applications of the crystal oscillators. Crystal oscillators are having an excellent frequency stability. So they are used in the generation of the carrier frequency in the radio transmitter and radio receivers. Okay, radio and not especially radio transmitters and TV transmitters, not receivers. So because of these oscillators are used to generate the excellent stabilized frequency. So because of the excellent frequency stability is achieved by using the special oscillator. These are used for generation of the carrier frequency, especially communication, radio and TV transmitters. So in temperature controlled movements, so these special oscillators can be used, and the precision electronic wristwatches and the digital clocks. So these circuits are used, and maintaining the precision time standards. These special oscillators will be used. Up to this, we have come to an end of the topic for crystal oscillator. So, can I solve this problem? Okay, go with the problem. The RLC circuit, electric equivalent circuit vibrational characteristics of the crystal oscillator is 4 megahertz. The crystals 4 megahertz crystals. So L is equal to 100 millihenry and R is equal to 100 ohms and C is equal to 0. C means CS. Okay, CM means CP. CP and CS. CS is equal to 0.01 picofarad and CS is equal to CS is equal to 0.01 picofarad and CP is equal to 5 picofarad. Now find the value of Q and then what is the stability factor? How much of stability? Solve this one. So next class we'll solve some examples on the all kind of oscillators like RC phase shift oscillator, wine bridge oscillator, Colpitt's oscillator, Hartley oscillator, and crystal oscillator. So next class we go with the some examples. Okay, problems. We are going to solve some problems. For that, I have to remember the frequency of oscillation of each and every oscillator. Formula for frequency of oscillation of each and every oscillator. Okay, then only it is easy to solve the example, some mathematical sums. Okay. Before that we see some frequency stability. What do you mean by frequency stability? So in case of all oscillators, we are the word frequently we use the frequency stability. Frequency stability. What do you mean by that frequency stability? So we'll get the stabilized oscillation from this oscillator. Stability is more important. Stability. What do you mean by frequency stability? The frequency stability is nothing but the ability of oscillator to maintain the constant frequency of oscillations. Simply remember, what do you mean by frequency stability? Is the ability of oscillator. So whether it is RC oscillator or LC oscillator or crystal oscillator, whatever the oscillator it is, then we can say it is a stabilized oscillations are produced by this only. The oscillator should be able to maintain the constant frequency of oscillations. The oscillator circuit should be able to maintain a constant frequency of oscillations. That is called as frequency stability. Okay, that is called as the frequency stability. Am I get my point? Are you get my point?
Yes, sir.
Are you able to get? Okay. So every time Prati oscillator circuit we are talking about this is the more stabilized oscillations will get frequently used that term. So what do you mean by frequency stability? Is the ability of oscillator that should maintain constant frequency of oscillations. Okay. So how much are able? It is according to that the ability of that circuit or that oscillator. That is we get the stabilized frequency or frequency stability achieved from that circuit. If it is able to maintain constant frequency of oscillation, if the design circuit is able to maintain constant frequency of oscillations, then we can achieve the frequency stability. So what do you mean by instability? Frequency instability. So over a period of time, the output of an oscillator may not be remains constant. Okay, actually, uh, practically, ideally it is upon. So ideally, it is a stable way. Every time we are going to say it is a stabilized oscillation, will get stabilized oscillation will get. But in case of the practical, there are so many reasons to get the frequency instability in oscillator. Okay, instability means the change in the frequency of oscillation in an oscillator over a period of time is nothing but instability. Okay, practically there are so many reasons uh, to get the instability in the frequency of oscillations. So what are those reasons? Let's look at examples one by one. There are 4 or 5 reasons are there. So that I'll tell you. Of course, this is a very important point. Okay, so because of we are talking about the oscillators. Oscillators are used to produce the oscillations. Okay, so the oscillation should be stable. Okay, then only that circuit will be used for the any applications. Okay, so then that is we saw the definition of the frequency stability. So, but ideally, we can say it is stable, but practically there are so many reasons. So, the output of the oscillator may not be remains constant. Okay, over a period of time because of the various reasons. So, what are the reasons? The first reason is the frequency of oscillation does not remain constant because of the change in the value of resistors and inductors and capacitors which are used in the any oscillator circuit, either it may be RC oscillator or LC oscillator or crystal oscillator. All oscillator tank circuit is made up of resistors and inductors and resistors and capacitors. Okay, so these are the elements which are used as a tank circuit elements. Okay, they are used in a tank circuit elements. So these elements changes their values with the temperature. The temperature is varied. Of course, if you operate all the equipments in room temperature, there is no problem. But if you operate at a low temperature or high temperature, such a case, there is a change in the value of resistors and inductors. So, if there is a change in the value of resistor or inductor, then there is a automatically change in the frequency of oscillation. Okay, that change is called as the frequency instability. So this is the first reason. The temperature is one of the main reasons. Now, what is the remedy for the temperature variation? The remedy for the temperature variation is in place of RC and LC circuit, the crystal oscillator can be used. Yes, sir. The crystal oscillator can be used, whose output is frequency remains more or less perfectly constant, even the temperature changes. So that's why we will go for the crystal oscillator circuit. This is the reason one. And second reason is operating point of an active device. So every oscillator circuit consisting of an amplifier. Okay. So to maintain the operating point is the constant. It is a very important task. Okay. The operating point of the active device or simply transistor is a very important. Okay. So the parameter of the transistor varies with the Q point. Q point means ICQ and VCEQ. If there is a variation in the value of ICQ and VCEQ, then there is a change in the value of Q point. Q point means if the Q point is stabilized, you will get the stabilized Q point, then the transistor will act in the active region. Otherwise, there is a change in the current or change in the voltage, the Q point moves whether into saturation or cutoff region. If it's saturation of if the Q point moves to saturation or cutoff region, there is a operating point as change in the fall in the value of the nonlinear portion of the load, which is in the effect of the frequency stability of oscillator. Okay, so oscillator either Q point to saturation region లోకి వెళ్ళిపోయినా either cutoff region లోకి వెళ్ళిపోయినా వచ్చే అవుట్పుట్ లో పీక్ లో మనకి కట్ అయిపోతుంది కొంత. పీక్ లో ఎప్పుడైతే కట్ అయిపోతుందో వచ్చే అవుట్పుట్ యాంప్లిట్యూడ్ పీక్ లో కట్ అయిపోతుందో ఫ్రీక్వెన్సీలో ఇన్స్టెబిలిటీ స్టార్ట్ అవుతుంది. ఓకే, దట్ ఎఫెక్ట్స్ ది ఫ్రీక్వెన్సీ స్టెబిలిటీ. దట్ ఇస్ అనదర్ రీజన్. సో అనదర్ దీనికి రెమెడీ ఏంటంటే then you have to maintain the Q point of an active device transistor is chosen such that confined to a circuit operation on the linear portion of its characteristics. ఆ Q point మనం కదలకుండా ఉండాలంటే Q values పర్టికులర్ గా లీనియర్ ఆపరేషన్ వరకే తీసుకోవాలి. అదొకటి రెమెడీ. దెన్ ఇంటర్ ఎలక్ట్రోడ్ కెపాసిటెన్స్. Already we discussed about this one. This is another reason. The power supply. There is a change in the DC operating voltages. Okay, if you operate VCC, if there is a sudden change in the VCC, DC operating voltages. So the active device shift the oscillator frequency. Okay, of course this problem can be used by regulating power supply. Another reason temperature variations are called some drift. Output load. The load, is there any change in the value of output load that may be caused change in the value of Q factor? The Q factor of the Q circuit is changes that affects the frequency of oscillation. That affects the frequency of oscillation. Mechanical vibration. So since mechanical vibrations are changing the value of the circuit elements, then they results the change in the oscillation frequency. So these are some causes or reasons for the frequency instability. But anyway, for any reason, there are some remedies that to follow those remedies to get the stabilized oscillations from all oscillator circuits. Okay, so with this, I'm going to stop at this particular point. And tomorrow, we'll discuss some. We're going to solve some problems. All of you bring your calculators and then take the notes, and then I'll give some problems and solve it, and then I'll take the answers, and then okay. Are you clear my point?
Yes, sir.
Okay. For tomorrow class, all you bring calculators. We're going to solve some examples and some problems on oscillators. Okay. Of course, you prepare these. Most probably, I'll keep the materials by today itself. So go through that material. If you are having any doubts, please feel free to ask to me, or you call me later. Anytime I'll available for you. So don't hesitate to call me. So anytime I'll answer your call. Okay. If there is any doubt. So because of so it is one of the important unit. So there is a simply will get 10 to 15 marks from this unit. 10 to 15 marks from this unit. Okay, very simple unit and easy to score the marks. Okay, I'll post the material today itself and prepare well, and then I'll go to solve some examples from today, next class, not tomorrow class, and then you ask me some doubts regarding any kind of oscillator. Okay, so with this I'll go to start and I'll take the attendance. Please respond very speedily. This attendance 64 is not there. Sorry, 65.
Present, sir.
7, 66, 7, 8, 9, 9. Speed. Please
66
unmute yourself and yes, sir. Like that. Please unmute yourself and tell your attendance. Next.
67 present,
present, sir.
Okay.
67 present, sir.
Next. Go ahead.
68 present, sir.
Then,
69 present, sir.
right.
70 absent, sir. 71 present, sir.
Okay, very good. Then,
42 present, sir.
right.
73 present, sir.
Okay,
74 present, sir.
right.
75 present, sir.
Right. Then,
76 present, sir.
right.
77 present, sir.
Right.
78 absent, sir. 79 present, sir. 80 present, sir. 81 present, sir.
82 present, sir.
Right. Then,
83 present, sir.
84 present, sir.
85.
86 present, sir.
Okay.
88 present, sir.
89 present, sir. 90 present, sir.
91 absent, sir. 92 present, sir.
93 present, sir.
94 present, sir.
95 present, sir.
96 present, sir.
97 absent, sir. 98 present, sir.
Okay.
99 present, sir.
Okay, right. Then A0.
sir.
A2 absent. Next.
A3 parents, sir.
Right.
A4 present, sir.
A5 absent, sir. A6 present, sir.
Okay, Namma, right. Right.
A8 present, sir.
Next.
A9 present, sir.
Right.
B0 present, sir.
B1 present, sir.
B2 present, sir.
Next.
E3 present, sir.
B5 present, sir.
B6
Next.
present, sir.
B7 present, sir.
B8 present, sir.
B9 present, sir.
B0 present, sir.
Okay, Namma. Next.
C1 present, sir.
Next.
C2 present, sir.
Right.
C3 present, sir.
Right.
C4 present, sir.
C5 present, sir.
C6 years.
Okay, right.
C7 present, sir.
Right.
C7 present, sir.
Okay, Namma.
C8 present, sir.
Okay, right. Okay, thank you all.